We speak about unraveling X-ray transforms on the Heisenberg group.
Cool. Yeah, thanks so much for the invitation. Yeah, this is a work that was largely done while I was at MSRI last year, and also partially supported by an NSF grant by Francois Menard. Just wanted to acknowledge that. So yeah, let's just get started. So the main idea of this project was to understand the X-ray tomography on the Heisenberg group, and really the main takeaway that we got was that what we'll soon define as the Heisenberg X-ray transform is injective. And here, we're just considering like L1 functions, nothing too fancy yet, and this lambda will parameterize a certain charge of geodesics. So in say like in a Euclidean case, this X-ray transform is very useful, just in X-ray tomography in general and medical imaging, and so we want to try to explore it in the Sub-Riemannian setting. So in the Euclidean case, the analog here is just the Radon transform in R2, which integrates either over straight lines or hypersurfaces. In this case, the same thing. So what we do is we parameterize the set of all oriented lines in R2 by some impact parameter S and some angle alpha, and fix some function and consider that function as a new function on the space of lines, where you take this function and integrate over that given line. And because this line integral of a function through some dense region is related to the degree to which, say, an X-ray will, the degree to which the intensity of an X-ray will diminish as it passes through a dense medium, this line integral is relevant to medical imaging, where we want to probe an invisible interior. So abstractly, this transform was first inverted in 1917, to my knowledge, and yeah, the Radon transform and X-ray transform both coincide in 2 dimensions, but of course the Radon transform takes on more of a group theoretic interpretation in higher dimensions. Now, moving away from the homogeneous setting, of great interest is the Radon transform is the X-ray transform on Riemannian manifolds, where we integrate over geodesics. So just take some scripted G to be the space of all geodesics. This is not necessarily a nice manifold, but it's at least a topological space. And fix some function and think of this function as a acting on maximal geodesics. So that this inverse problem has a standard tool bag of questions that we want to answer. And the first and foremost is injectivity. Can we theoretically reconstruct this function given its X-ray transform IF? So yeah, but even if we can do this, it might not really be practical. For example, this problem might be very highly unstable. So that's really for practical purposes, the next question we'd want to answer is stability. How sensitive, if we can invert F theoretically, if we can invert this X-ray transform theoretically, how sensitive is that inversion to error? And from a functional analytic perspective, that's just asking, in what topologies is this I bounded below with respect to? Usually it'll be some Sobolev space. And beyond that, we may want to find out what, after deciding on what some natural domain is, it may not be compactly supported functions. After we decide on some nice domain, then we might want to know exactly what the range is. And beyond that, we would want to find out some inversion formula, or at least some technique to approximate the inverse of this operator. Usually we don't have inversion formulas unless we're in highly symmetric settings, such as if this manifold is a group or something like this. So generally speaking, on Riemannian manifolds, the question of injectivity of X-ray transforms generally, yes, whenever our geometry has a lot of convexity. And in particular, whenever this geometry has a lack of conjugate points. So conjugate points are generally a bad idea, bad for inversion. Just say that we have two conjugate points on a Riemannian manifold. And if I want to try to understand like what a function looks like at some conjugate point over here, well, if I'm integrating with respect to geodesics here, and I vary this geodesic, then I somehow lose a degree of freedom at this first conjugate point in order to probe for information. And so for this reason, this geometric reason, conjugate points are a bad idea for inversion. Hang on. Let me get rid of this. Didn't realize this would carry over. So more generally, aside from just Riemannian manifolds, the X-ray transforms have been studied on, like the magnetic case where we integrate over magnetic geodesics, symmetric spaces, and even with respect to Yang-Mills geodesics, where we have like a lot of generic answers to whether or not something is injective, but we don't really have inversion formulas because these geodesics are so complicated. But yeah, not studied very much is the Sub-Riemannian setting, which in some case encapsulates all these previous cases that are pretty well studied. There has been some work. There has been the transversal radon transform. So just take the set of all planes in R3 that intersect the z-axis. And if you know the integral of a function on R3 with respect to all these planes, can you invert this function or recover this function? Strickart's studied the so-called D-plane transform on the Heisenberg group, where on an n-dimensional Heisenberg group, you integrate over hyperplanes of a certain planes of a certain codimension. And also like mean value transforms have been studied on Heisenberg groups too, where you integrate over circles that are tangent to the distribution, or that live inside planes tangent to the distribution. But in none of these cases has anybody really, to my knowledge, studied geodesic X-ray transforms on the Heisenberg group. So let's move in, just set up some notation then. The Heisenberg group is obviously a very natural place to start studying integral geometry on sub-Riemannian manifolds because it's the simplest non-trivial example. So just setting up some notation here, we define our geodesics as projections of integral curves for a Hamiltonian flow. And since this is a local model for three-dimensional sub-Riemannian manifolds of contact type, hopefully techniques developed here can be used in more general settings. So here's a picture I took from Montgomery's book, just to make sure we all have a picture of what these geodesics look like. And I'm going to call this, the charge of these geodesics lambda, which is just the inverse radius of the project circles that these geodesics project to. And so I'm taking some function in the Heisenberg group, and I want to know, if I know its line integrals with respect to all curves, all helices of this form, and I've recovered this function. So first step is to write down this X-ray transform concretely. So for every charge lambda, let's just set a model geodesic centered, whose axis is centered at the origin. And so it looks like so. And every geodesic on the Heisenberg group whose charge is non-zero is a left translate of one of these gamma subscript lambdas here. So I'm going to think of the space of geodesics on the Heisenberg group as sort of foliated, foliated by leaves of some fixed charge lambda. And I'll call each one of these leaves G subscript lambda. And I can, because of this left translation property of the Heisenberg geodesics, I can parameterize all the geodesics by elements of the Heisenberg group itself. And there's some non-uniqueness in this parameterization, and that's captured by this discrete subgroup lambda. because these geodesics are helices, it makes sense that this discrete subgroup, whenever you translate up one of these geodesics by this fixed amount, you arrive at the same geodesic. So in sum, we can parameterize all the geodesics by these variables, complex variable z and t and lambda, and write the X-ray transform this way. And it's well defined as long as f is a compactly supported continuous function. So here's also an image I got from the University of Birmingham webpage. The main challenge that we face in the sub-Riemannian case again is the presence of conjugate points. And here just sort of looking at the Heisenberg wavefront set and seeing how it instantly self-intersects gives sort of an idea of this zero radius of injectivity. In the inverse problems community, we have these standard tools called Pestov identities or Helgason type support theorems that largely rely on a positive definite second fundamental form or some strong convexity assumptions to prove that various X-ray transforms are injective. And we simply, without a closer look, these tools don't necessarily apply. So the first step we could give the first thing we could maybe try is a global harmonic analysis technique, which I'll explain in a moment. So just to give a little bit more information on the main result again, we know that the Heisenberg X-ray transform is injective, or we will show that it is. But in particular, we know that you really only need to know the line integral of some function over geodesics of arbitrarily small charge, which essentially makes sense because since the dimension of the set of geodesics on the Heisenberg group is 4, and we have some function on the Heisenberg group, that's a function on 3-dimensional space, the problem is overdetermined in a way, and so we really don't need all the information of line integrals to recover a function. Yeah. So the main tool at our disposal to prove injectivity is something I'm calling the Heisenberg-Fourier slice theorem.
Sorry. Can I ask a question?
Of course, yeah.
Can you go back one slide, please? So you said that you need to know that that you say that if E lambda is 0 for lambda in the neighborhood of 0, then f is equal to 0, but it is not enough to ask that lambda is that E lambda of f is 0 for lambda equal to 0, right?
Yeah, it's not enough for lambda equal to 0.
Okay.
Strickhart's actually, for this case, so when lambda equals 0 and we're just integrating over straight lines,
Right.
Strickhart's was able to write down a spectral decomposition of this operator and found that it has a non-zero kernel. Yeah, so we do indeed need some positive lambdas to recover this function.
Okay.
Yeah. But thanks for asking. So the main tool that I'm using here is this operator valued Fourier slice theorem. So it's just on one hand, it's relating the what I'm calling like a reduced Fourier transform f lambda. On one hand, we're relating the Fourier transform of the X-ray transform to the full Fourier transform post-composed with some operator that I'm just for now calling an operator valued Bessel function. I'll sort of define all these terms a little more clearly in a few minutes. But the idea is that knowledge of the X-ray transform of some function f with respect to some fixed charge lambda tells you the Fourier transform of f for some lattice that scales some integer lattice that scales according to lambda. So the more lambdas we have, the more like discrete samples we have in the Fourier space, and so once we have enough lambdas sufficiently small, we can recover this function. So let me just define some of these terms that you're seeing here. Oh, sorry. Let me take a step back a second. So the Euclidean version of this strategy is the is also called the Fourier slice theorem or the projection slice theorem. And essentially, it's relating the Fourier transform of the radon transform. So if you have given the radon transform of some function f, if you take its Fourier transform in the impact parameter, then this is somehow related to the full Fourier transform. And so what this looks like geometrically is if you have, say, some function in position space. Say this is R2. And along some fixed direction, alpha, we collapse this function. So if we integrate this function along all lines perpendicular to this direction alpha, then in frequency space, so let's pretend we're dealing with a Gaussian, so it's the same in frequency space. Then in frequency space, this is the same as in that direction alpha, just taking a slice. So this is just, this is just expressing as another duality of the Fourier transform. Okay. And so this is helpful for proving injectivity, because if we know that the radon transform of some function is 0, and we know that its full Fourier transform has to be 0, and so the function itself must be 0. That's the main thrust of the Fourier slice theorem. Okay. Sorry about that. Apologies. So just to define what some of these tools are exactly, let's just recount some of the harmonic analysis on the Heisenberg group and start by defining its representation theory. So let scripted H be the Bargmann-Fock space, just the set of all holomorphic functions with some Gaussian decay. And let's define this family of Fock representations on the Heisenberg group, just strongly continuous homomorphisms from H into unitary operators on this Hilbert space. Defined accordingly, but don't stress too much about what the exact form of this formula. The main thrust is that this is a unitary representation of the Heisenberg group, and every unitary representation that does not vanish on the center is equivalent to one of these. So we have, we essentially think of the Pontryagin dual of the Heisenberg group as R star. And we use this family of representations, to define a Fourier transform in this way. Also, as a side remark, for any other authors who use, say the Schrodinger representations to define a Fourier transform, this entire analysis is equivalent up to conjugation by a unitary intertwining operator. So this is our Heisenberg Fourier transform, where this unitary representation takes the place of a Fourier mode. This Fourier transform has most of the usual properties of the classic Fourier transform. For a nice enough function, the image of this Fourier transform is also nice. For some Schwartz function, the Fourier transform is a Hilbert-Schmidt operator. There's a Plancherel theorem associated with this Fourier transform, and also an inversion formula. Here I'm being a little cavalier about what the actual target space is, but it's not very important at the moment. And this, this Fourier transform can actually be used to, it can be extended to tempered distributions, and it can also be used to define, pseudo-differential operators adapted to the Heisenberg group, and maybe hopefully FIOs as well. So just giving a little more information about this Fourier slice theorem and what it's saying, where it comes from. Let's just start by taking a look at the X-ray transform for some fixed charge lambda, and it's a map from L1 on the Heisenberg group to L1 on the space of geodesics, and the content of that is just Fubini's theorem. So the idea here is to identify the space of geodesics as a quotient of the Heisenberg group. This is really just like an orbit stabilizer isomorphism, and that allows us to give a concrete meaning to the space of geodesics. And now our X-ray transform I is just a map from L1 of one group to another. And we can actually decompose the X-ray transform into two maps. One I'm calling P, it's a periodization map. And then this other map I, which is just a reduced version of the X-ray transform. And I'll explain these both a little bit more later, but this P sort of captures the periodicity of Heisenberg geodesics, whereas this I tilde just captures the holonomy, or one period of these geodesics. So we're really just factoring through a quotient here. If we apply the Fourier transform to L1 functions on the Heisenberg group, by an analogous result from the Euclidean case, we can think of the image of the Fourier transform as continuous operator valued functions on R star, taking values in compact operators on Fock space. And analogous to the way that the dual of a circle is discrete, we apply this reduced Fourier transform to L1 functions on the quotient, and we get some discrete family of compact operators as a result. And now in these generalized frequency domains, this periodization map is really just a restriction map. And this I tilde, this reduced X-ray transform I tilde, is just some kind of generalized Fourier multiplier, where the Fourier multiplier is denoted by 2 pi lambda over lambda script to Jn. And the idea is just to study what these operators look like in frequency space. And also the content of the Fourier slice theorem is really that if you follow this diagram in 2 different directions, first go right, then go down, or the other direction, going down and then right, you get the same result. This diagram commutes. So just giving a little bit more information about this, this identification of the space of geodesics. Again, we fix this family of model geodesics, and we have this parameterization that's unique up to some discrete subgroup. And so we can identify geodesics with cosets. Something that's interesting to note, whenever we identify the space of geodesics of some fixed charge with this quotient space, then actually the X-ray transform I intertwines the sub-Laplacian with a wave operator, where this wave operator is understood as acting on functions on this quotient. So just an interesting abstract fact about this X-ray transform. So one other ingredient for this Fourier slice theorem that I've been throwing around quite a bit is the what I'm calling the reduced X-ray transform, and it's just the analogous to the full Fourier transform, where instead we only take a discrete subset of their unitary representations, and that discrete subset are exactly the representations that descend from the full Heisenberg group to the reduced Heisenberg group. They're the ones that respect the symmetry of this subgroup lambda or gamma subscript lambda. And strictly speaking, this Fourier transform is non-invertible because it doesn't take into consideration finite dimensional representations. The finite dimensional representations don't matter on the full Heisenberg group when you're considering like the spectral decomposition of a function, but on the reduced Heisenberg group they do matter. But nonetheless, we don't need to consider them at this moment when we're defining the Fourier transform. Okay, so given all these ingredients, one more thing, just giving a little more information on this decomposition of the X-ray transform. So we have this map P subscript lambda, which I'm calling central periodization. Just take some function and sum it in the central direction, and let this map I tilde simply be integration with respect to just one period of these helices. And so in a way, this P captures periodicity, whereas this I tilde captures the holonomy of the Sub-Riemannian geodesics. So breaking down the X-ray transform into this I tilde and into this P lambda, it becomes a little bit more digestible. This I tilde is actually a Fourier multiplier in a generalized sense. And the Fourier multiplier corresponding to it is exactly this operator valued Bessel function J. And the reason why I'm calling it an operator valued Bessel function at the moment is just because it's an integral over a unitary it's an integral over a family of unitary operators over a compact set over a circle, which is analogous to the way you could define like a Bessel function as integration of a plane wave over a circle. So on one hand, we have that I tilde is a Fourier multiplier, and on the other hand, we have something that looks a bit like a Poisson summation formula. I haven't found a reference for this in the literature, but I'm sure that I'm not the first to write something like this down, where if you take some function on the Heisenberg group and you apply this periodization map, and then you post-compose that with a reduced Fourier transform, that's the same as just taking the full Fourier transform with some rescaling. So putting these two pieces of the puzzle together, we have the full Heisenberg Fourier slice theorem on the Heisenberg group. And the way we use this identity here to prove injectivity is to analyze this operator Jn. And in fact, it's very nice. It's a compact operator. It's essentially an off-diagonal countably infinite matrix. And just by looking at the singular values of this operator Jn, which really just consists of combinations of Laguerre polynomials, we can actually show that this Jn is an injective operator. None of the singular values are 0 whenever n is an odd integer. I'm leaving out the details of that part, but it's simply a number theoretic argument. So knowing that this Jn is injective most of the time, we can prove injectivity. We do it like this. Let's suppose that we know that I subscript lambda f is equal to 0 for all lambda in some epsilon neighborhood of 0. Well, then the left-hand side of the Heisenberg Fourier slice theorem is 0, and we're left with this right-hand side. So if we know that, so what I mean to say is, if we know that this Jn is injective for some odd integer n, then in fact we know that the Fourier transform of f at some number h is equal to 0 whenever h varies in some interval from 0 to n epsilon squared. And we take the union of all such intervals as n varies over odd integers. And this just recovers all non-zero real numbers. And so using the Heisenberg inversion theorem for the Heisenberg Fourier transform, we can see that f has to be 0 almost everywhere. So that's the main way that we use the Heisenberg Fourier slice theorem to prove this result. So we can play the same game with some the compatible Lorentzian and Riemannian metrics as well, where I haven't written down the corresponding Fourier slice theorems, but we have a similar result where if we take some I epsilon, where epsilon corresponds to some say Riemannian metric that's approximating the sub-Riemannian metric, then for any epsilon, we still can recover some function f with geodesics of arbitrarily small charge. It's been known already that a function can be recovered on the Heisenberg group from its geodesics with respect to a left invariant Riemannian metric, but I think this refinement is new. And we have a similar statement for Lorentzian geodesics too. And in fact, we can specifically recover a function on the Heisenberg group with space-like Lorentzian geodesics. And really the reason that this is true is that space-like Lorentzian geodesics are those for which the charge lambda is arbitrarily small anyway. And time-like Lorentzian geodesics do not give you enough information. Yeah. So just to give an example of the robustness of this technique for improving injectivity. So some things that I'm still working on are, proving, injectivity was proven from a number theoretic argument, so it might not actually be practical to invert a function on the Heisenberg group. It might be an unstable inverse problem. So currently trying to formulate a stability statement. And a key idea here is using the intertwining properties of this X-ray transform to define, on one hand, a Sobolev space, the usual Sobolev space with respect to the sub-Laplacian in the domain, and some other Sobolev space that respects this wave operator in the target space. Some other, to really feel like this project is done, would be nice to have an explicit inversion formula. In the Euclidean case, there are really nice inversion formulas for X-ray transforms that involve powers of the Laplacian. So if there was some nice functional analytic, if there was some nice spectral function of, say, the Laplacian and the Reb vector field that would give you the X-ray transform, that would be really nice. And also, it shouldn't be too hard to push this result. Use the fact that the Grecian plane is a quotient of the Heisenberg group to push this injectivity result down to the Grecian plane as well. And same with other types of quotients of the Heisenberg group. For example, just the Heisenberg group modded out by a discrete subgroup of its center. And how am I doing on time? Okay.
You're still 20 minutes.
Okay. Yeah, like we finished a tad bit early, but another note on the X-ray transform on the reduced Heisenberg group, just as an extension of the X-ray transform on the full Heisenberg group. Much like the Euclidean case, we can define an X-ray transform on a torus, and we keep track of geodesics with rational slope being the ones that actually close up on a torus. And we can ask whether or not a function on a torus can be recovered from integrals over closed geodesics. We can do the same thing on the reduced Heisenberg group, where if, say, I take, let's say we're on the reduced Heisenberg group. Here we're identifying here and here. And if I have some geodesic, say that winds a certain number of times like this, I might say that this geodesic has say a horizontal winding number A of 2 and a vertical winding number B of 1. These numbers are just keeping track of I'm saying that this horizontal winding number is just in one period how many counterclockwise rotations this geodesic makes around its central axis, and defines vertical winding number to be in one closed period how many times the geodesic passes through this S1 component of the reduced Heisenberg group. And yeah, so as long as as long as these numbers are integers, then, as long as these numbers are integers, then we have a closed geodesic. And the period of such geodesics, after staring at it for a little while, is 2 pi times the geometric mean of A and B. And we can play the same game and ask whether or not this is a injective X-ray transform. And we can't actually say a lot about this. We can essentially write down a singular value decomposition for this operator, which is a little bit easier than the full Heisenberg group case, because we have essentially compactified the problem in a serious way. So what we get here, we have these functions psi with these 3 subscripts n, j, and k that form an ortho. I haven't written them down explicitly here, but these are an orthonormal basis for L2 of the reduced Heisenberg group. And this 0 I'm placing on L2 just means that I'm considering functions whose integral through the center direction is 0. So if we take this natural orthonormal basis for L2 functions on this quotient of the Heisenberg group, then we actually have a very concrete singular value decomposition. And in some sense, what this looks like is, if we look at the Heisenberg fan, I tend to mix these spectra, but if on one hand we have take an axis where on one hand we have the spectrum of the sub-Laplacian, and on, say, the x-axis we have the spectrum of the Reb field, or the central vector field, and we have these rays whose points correspond to joint eigenvalues for these 2 operators. Then on the reduced Heisenberg group, we just take a discrete subgroup of this fan. And I'm being a little cavalier about where these points are. What it turns out this X-ray transform is doing is it's acting in some way like a ladder operator. So it'll take you from an eigenspace corresponding to one of these points to, it'll jump you up to some other eigenspace here. Being a little cavalier as to exactly how this works, but there's something interesting going on here, and I haven't quite digested this connection. But yeah, there's still like a lot of interesting things to learn, even in the Heisenberg group case. Okay. Then, so some places I'd like to go eventually would be to look at the same question, perhaps on some 3-dimensional contact manifolds. At first, maybe ones with a lot of symmetry, like SU2, SL2, or the special Euclidean group, or just try to study the same X-ray transform on other Carnot groups, in particular, say, the angle group or H-type groups. And farther off, I think some really interesting questions would be to move away from the homogeneous setting and study questions like boundary rigidity. So in the inverse problems community, it's a difficult and interesting question is to determine if you have, say, a manifold with boundary and the metric on this boundary. Can you determine up to diffeomorphism the metric on the interior of your manifold? And so the X-ray inverting the X-ray transform is somehow a linear version of this nonlinear boundary rigidity problem. So yeah, I mean, farther off, it would be nice to think about this kind of question on a sub-Riemannian manifold. On some sub-Riemannian manifold, knowing the boundary distance function. Is it under what conditions can we actually recover the metric inside? Anyway, that's the remainder of the talk. Thank you for your attention. Yeah.
Thank you. Yes, clapping is more complicated on this